All right, so let's think about a evaluation metric that is not susceptible to this problem of an imbalanced corpus and misleadingly high accuracy or misleadingly high score on an imbalanced corpus. And to find a good evaluation metric, we look to the search engine or to the retrieval community because they have similar problems of imbalancedness, and they have developed a couple of measures, and we'll look into those. So typically when you're in a case of a search engine like Google, what you type in is a couple of query words and you get a couple of results. Basically, what Google is doing, it's searching for relevant documents in a large, in this case, relevant web pages in a large collection of web pages. And the number of relevant documents is usually very small. And we do have exactly the same problem of imbalancedness, namely that a classifier that gets every document, that classifies every document as irrelevant, would achieve almost 100% accuracy, let's say 99.9% accuracy, because almost all web pages are irrelevant for our query. So again, we would have misleadingly high accuracy. And therefore, we need to have measures that can reflect this setting. And the measures that have been developed are called precision and recall, and then they are merged into one single measure, which is called the F1 score. And what is the precision? Precision can be framed easily as saying we check how many documents did the search engine actually retrieve. Let's say it retrieved 4 documents, and out of those 4 documents, 3 are actually correct. So they're actually relevant documents, and 4 have been retrieved. So this is the precision. The recall is how many relevant documents are there in total. Let's say there are 8 relevant documents in total, out of which 3 have been retrieved. So it would be 3/8. Then we have the F measure, which combines both metrics into a single score. So we have precision and recalls, combining them into a single score using this formula here. However, this is a little bit difficult to memorize. So what you can instead also memorize is that it is the harmonic mean of the precision and the recall. And the harmonic mean of any 2 numbers, P and R, is given by this formula on here. And what is interesting about the harmonic mean, the interesting thing is that it's closer to the minimum of 2 numbers. And it's also worth pointing out that there are many different means, the most popular being the standard arithmetic mean of P and R, which would just be P plus R divided by 2. The arithmetic mean has the property that it's close, it's exactly in the middle of the 2 numbers, right? Whereas the harmonic mean has the property that is closer to the minimum, which then means that you cannot easily trade off one of those measures for the other. For example, with the arithmetic mean, you could be very good on precision and then make up for a very bad recall. With a harmonic mean, you can't do this. So for example, if we have a web engine that retrieves everything as positive, so it has a huge recall, it has perfect recall, because there's actually not a single document that is not retrieved. So all documents on the web, on the web are retrieved. So this would have a recall of 1, but it would have a very bad precision, and you should not be able to trade this off. So if we do the F1 score, it would be the final score would be close to the minimum score, which is the precision score in this case, and which would be very bad. Now, precision and recall can also be read off by this 2x2 contingency table, which is shown here. In this table, we have the model predictions and we have the gold labels. And for example, the prediction could be that it's positive. So this is one class 1, this is class 0 down here. Could be class 1, so we have a prediction of 1. And then the true positives is here, where the gold label is also 1. So so we have a match. This document is both retrieved and it is relevant. In the case where the document is retrieved, so the prediction is 1, but it's irrelevant, where in the case of the false positives, then we have the false negatives, where the element is predicted to be, is not retrieved, but it's actually relevant. And we have the true negative, that's also a good case, where we have the document is predicted not to be, or the document is not relevant, it's predicted to be 0. So it's not retrieved, and it's also irrelevant, the gold label is also 0. So in the search engine community, this case here is not so interesting because we're mostly looking at the documents that are actually that the search engine actually retrieves, not at the document that the documents that the search engine does not retrieve, and are also irrelevant, right? Those case is the majority anyway, so they're not so much interested in this setting. So how can we generalize this from a binary setting, retrieve, not retrieve, relevant, not relevant, to a multi-class setting where we have multiple classes? In this case, we can get a precision and a recall for each of the classes. So let's assume we have a gold setting, gold labels of 1, 2, 3, and we have predictions 1, 2, also 1, 2, 3 in different forms. We can get the confusion matrix from NLTK, compare the gold to the retrieve to the printing, and we would get such a contingency table. So what we see here, so now here, note that the true class and the predicted class is inverted. Before we had the predicted on the columns. So this was predicted before, this axis was predicted before, this was true before, now it's inverted. Unfortunately, to get the accuracy of such a model, we would check the diagonal, because on the diagonal we have all those cases where the model prediction, the true class coincides with the predicted class. So the model says the true class is 1, the model says 1, the true class is 2, the model says 2, the model says the true class is 3, the model says 3. So we have 2 plus 1 plus 1 divided by all the entries. So that is like 2 plus, this is 3, 4, 6, 7, 8, 10. So we have 10 instances over all the dots stands for zeros here. So we have an accuracy of 40%. If we want to get the precision, then in this case, before we had looked at a row when it was inverted. Now in this case where it's the other way around, we look at one of the columns. We get the precision for class 3. Let's say we focus here on class 3. So we check all the cases where the prediction is class 3. There are 2 cases where the prediction is class 3 and 1 case is correct. So we got a precision of 50%. If we look at the recall, we look at the row number 3 for class number 3. We say that there are overall 3 cases where 3 cases of class 3. So these are those 3 cases of class 3. One of them is correct, so we have 1/3 as a recall. And then we have, so to summarize, we have the accuracy, which is the fraction of correctly classified items. We'll find this on the diagonal there. Those items are correctly classified out of all items. We have the precision for class 3. This is those, this is a fraction that are predicted as class 3. So 2 are predicted as class 3, 1 actually belongs to class 3. We have the recall for class 3. This is the fraction that belong to class 3 that are actually predicted as class 3. So we have 3 that actually belong to class 3, and one of them, we have 3 instances that actually belong to class 3, and one of them is actually predicted as class 3. This is the recall for class 3. We can get a recall and precision for each class, also for class 2, for class 1. And finally, then we can get an F measure for all of those 3 classes. And then finally, we can make a macro F1 score that is averaging the F measures for all 3 classes. In this case, we have 3 classes, but more generally, we would have N classes.